Yeah, hi again. In this video, we continue with linear programming. So if you remember, the requirements for an LP problem or linear program is we want to maximize or minimize some quantity. There will be restrictions or constraints that we need to factor in. And so there will be some alternative course of actions to choose from. These are called the decisions, and we have to express the objective function and the constraints as linear equations or inequalities. So to put these things together, we have to let's talk about the components of an LP then, which we talked about before. So this should be a review. First, we need to identify the decision variables, the objective function, and the constraints, which includes both constraints on resources and non-negativity constraints, right? Just to give you an idea, when you have a problem, how do you go about modeling it? Because this is really the key part. Modeling the problem is the most important aspects of a linear program. Because if you solve the wrong problem, you're not going to get the correct answer. So first, if you have a problem, you're going to read the problem first time to get a general idea of what the problem is. Read it again with an idea, or try to identify what your decision variables, what's your objective function, and what's your constraints, and what's your data elements. So when we talk about decision variables, we need to use mathematical symbols to represent the level of activity of each one of them, like x1, x2, x3, and so on. And we need to determine the quantities to be determined, so the values of these decisions when we optimize the problem. The objective function is usually the quantity we want to maximize or minimize. And it should be in the form of a linear relationship. The constraints also should be linear relationships, and they can be either less or equal, greater or equal constraints. So they are inequalities. And it would be helpful to attach a word description for each constraint. What does it do? This constraint is basically the first plant constraint, or puts restriction on the resource of the plant you cannot exceed, and so on, like the problem we had. The data elements, these are the inputs, the coefficients of the variables. The right hand side, these are the resources available, B1, B2, B3, B4, and so on. The coefficients of the decision variables, these represent either profits or costs, so we have to identify those carefully. And also the coefficients of the decision variables and the constraints are usually technological coefficients that don't change from time to time. And so you want to put all these things together and formulate the problem mathematically. So you need to have a mathematical formulation for this problem. Okay, once you have the mathematical formulation, now we're going to solve the problem. And I want to solve the problem we had, the snowmobile problem, graphically, or sometimes it's called the graphical method or the corner point method. And the basic idea of this is the following. You want to graph the constraints, and so you need to be able to graph equations of straight lines and also inequalities. So if you don't know how to do that, it's the time to go back and review how you do this. I'll review it quickly as we go along. Draw the family of lines, each member of which is defined by the objective function. So first, let's go back. So first you draw all the constraints that determine the feasible region. Then you take the objective function and you draw a family of lines for different values of the z, or the objective function, and these lines will be parallel to each other, and they will intersect the feasible region at different points. So you're going to keep moving that line until it meets the feasible region exactly at one point, and that would be your optimal value. So if we go back to the snowmobile, apply these ideas to the snowmobile production problem. Remember, we had, this is the feasible region, so let me show you how we graph that. And here we have the constraints. If you remember, so our first constraint, it was 2x1 less or equal 300. So now I want to graph that. 2x1 equal 300 would be this line at 300. And also so that means x1 equal 150 basically, so that's the point 150. And then I want the less, or when I have the less or equal, so that becomes a region which represents this region. That's why this arrow is here. So that would be, my graph would be everything on this side. Then I go to the second constraint, which is 2x2 less or equal to 540. So I graph the line 3x2 equal 540, which would be this line. Then my feasible region should be on this side of the line. So now I'm limited to this part and this part here. So I go to the third constraint, which is this one here, 2x1 plus 2x2 equal to 440, which would be this line, C3, and I should be on this side. How do I know which side of the region I pick? So I usually pick 0, 0, and if it satisfies the constraint, I will be on the side of the 0, 0. If not, I will be on the other side. So in this here, 0 plus 0 less, this is less than 440, so I should be on this side where the origin is. And so I go to the third constraint, which would be this one here. I graph that. And then I have my non-negativity constraints, x1 greater or equal to 0, which means this line, and I should be on this side. And the last one is x2 greater or equal to 0, so that means I'll be on this side of that constraint. And so if I shade all the area that's satisfied by all constraints, it gives me this shaded area. So we know now I have to find the intersection of each of these two lines, because these corner points, so I have here 1, 2, 3, 4, 5 corner points that are corner that bound the feasible region. So this corner point is the intersection of these two lines, this corner point is the intersection of this and this, and this corner point is the intersection of this line and this, and so this one. So we have to, and that means we can find each corner point by solving the corresponding two equations and two unknowns. So you have to be able to solve two equations and two unknowns. You got all the corner points, and then you evaluate the objective function at each one of these corner points and pick the corner point that gives me the maximum value. Also, we can take the objective function, which is, my objective function is this, z equal 50x1 plus 40x2. I can graph that when z star equals 0, so that gives me a line at the 0 like this. Then I make this 50 maybe, and then graph that line, and that's going to be another line parallel to it. It's parallel because the slope in this case, which is negative 50 over 40, will not change. And so this will give me, as I change these stars, going to give me a family of parallel lines. So I move and the value of z goes up as I go in that direction. I keep moving that line, and that's the red line here, where it just touches my feasible region at one point, the corner point. And if I move the line up there, I will become unfeasible. If I move it in, I can do better by moving it back in that direction. So that's my optimal solution. So that line now so this point is the solution of these two equations, 2x1 equal 300 and 2x1 plus 2x2 equal 440. So I solve these two equations in two unknowns. Luckily this equation has only one unknown, so 150 and 70, which is what we had before. And so we evaluate z star at 150 and 70, and that gives me 10,300. Okay, so that's this graphical method, and that how it works. So what you need to do is to practice this with at least one problem, or do it yourself to make sure you understand this method. So the limitation of this method, it works only for 2 decision variables. If I have more than 2 decision variables, I would need a 3-dimensional graph to do this. If I have 4 decision variables, I need to have 4-dimensional graph. Well, that's not really even possible to imagine a 4-dimensional graph, let alone if I have 100 decision variables. So I would need a 100-dimensional graph. And so it works for 2 decision variables and nothing beyond that. So what to do? Let's see. First, let's summarize what we learned with this method. So solving by the graphical method means plot the constraints, equations, identify the feasible region, and an optimal solution is guaranteed to be at a corner point. So identify all corner points, calculate the objective function at each corner point, and then the best value would be your optimal solution. Okay. So when I have more than multiple decision variables, there's something called the simplex method. It's a very powerful technique that was developed by George Dantzig in late 40s, and actually most computer based LP packages use this method, the simplex method. There are other methods, but this is really the most popular and easier to work with. And Excel Excel Solver has this method. So in this case, we're going to use Excel Solver. So please view the video in Excel Solver how to run the simplex method on Excel Solver. Okay. The way the simplex method works, let me explain that graphically in the 2-dimension method, and then we talk about it algebraically. If I go to my graph, the simplex method always starts at the corner at the 0 point. In this case, as if so at x we assume x1 x2 equals 0, and that's where we start. And then what the simplex method is set up is to solve systems of linear equation and decide how I can improve my objective function. And in this case, I can move in this direction and move all in this direction. So I only move along border lines to new corner points. And then the simplex method says, well, if you move in this direction, you should stop here. And there's a rule for that, identifies where I stop. So I move. So I have a choice, and basically I pick the direction that gives me the maximum increase in my objective function. I go up to this point, and then I repeat. So I check that this point is not optimal because I can improve. So then I have a choice of moving in this direction or in this direction, and then the simplex will say, well, let's move in this direction, and then let's stop at this point, and then now we are at this point, which is better than this. The simplex always improves the objective function at each step. Now at this point I can move in this direction or in this direction. So the simplex method checks and says, if I move in this direction, I don't improve my objective function. If I move in this direction, I don't improve my objective function. Therefore, this must be my optimal solution. So I stop there. And of course, you can imagine if you have 100 dimensions and you're at this point, so you have 100 different directions to move along. And that's what the simplex method takes care of efficiently. Okay. So a couple of things to learn that we will need for sensitivity analysis. We need those about the simplex method. Is this first how we need to set up the problem to make it suitable for running the simplex method. So first we associate with each feasible point a slack, which is the slack is associated with a less or equal constraint, and we associate a surplus variable for each greater or equal constraint. So slack is the amount of resource that's left over at a given point. We haven't used that resource fully. So if a slack is 0, what does that mean? We answered that for you. That means we used all that resource. Surplus, on the other hand, is associated with the greater or equal constraints, which means it represents the extent to which some minimum restriction is exceeded at a given point. So if my restriction is to meet the demand at a point and I ship more product than is needed, the extra would be my surplus. Okay. So the way we implement this is as follows. So I have my problem now. Let's do that with our example. Maximize 50x1 plus 40x2. 2x1 is less or equal to 300. We rewrite that as 2x1 plus s1 equal 300. So s1 is my surplus, and so the difference between these two is my s1, and we call that the slack. Right? Same thing here. So 3x2 less than or equal 540 becomes 3x2 plus s2 equal 540. This constraint becomes 2x1 plus 2x2 plus s3, so that's the slack for the third resource, is 440, and the fourth constraint is 1.2x1 1.5x1, and then I add the fourth slack, which is 300. So a corner point is sometimes also called algebraically in the simplex method a basic feasible solution. So it's a feasible solution, which means it's in the feasible region, but also it's a corner point feasible solution. So it's one of these corner points in my graph, and that's the definition, which means, because if I have a problem with n constraints, with n decision variables and m constraints, so when I add all my slacks, so I'm going to add m slacks, so I end up with m plus n variables. So at any given point, I would have n of those variables would have 0 values, and m would have non-zero values. So we call them non-basic variables. The 0 values are called non-basic variables. The non-zero or 0 variables, and the non-zero are called basic variables. Okay. So this would be my maximization problem. I have m equal 4 basic variables and n equal to 0 variables. So my starting point in this is I would let x1 and x2 equal 0, and my corner point would be s1 equal 300, s2 540, s3 440, s4 300. That's called a basic solution, a basic feasible solution, and then that's my corner point, and then I decide to move along the corner points. I don't think we need to go much deeper than this with the simplex. Now if I have a minimization problem, instead of giving you a new example of a minimization problem, I want to take the same problem we had here and write something called the dual of this problem. The dual of a problem is created by minimizing a w, which would be now I create for each constraint I have a corresponding variable. I call it y1, y2, y3, y4. So in my dual problem I have 4 variables, y1, y2, y3, y4, and I create a minimization problem by taking 300 times y1, 540 times y2, 440 times y3, and 300 times y4, and my constraints would be 2 y1 plus 0 y2 plus 2 y3 plus 1.2 y4 would be greater or equal to 50. So that's where the 50 comes here. And then I have 0 y1 plus 3 y2 plus 2 y3 plus 1.5 y4 greater or equal to my second coefficient 40. So I have 4 constraints, then I end up with 4 dual variables. I have 2 variables, that means I have 2 constraints. My constraints are less or equal here, and then mine here are greater or equal. So in this case, to set up this problem, I would instead of adding slack variables, I subtract surplus variables. Okay, now I'm still looking at the difference between this side and this side, so I have to subtract the difference to make this an equality constraint, and that's the surplus. And the same thing, I subtract this to get the surplus. So now if I proceed the way I did before, so I set up my variables equal to 0, that would give me as a starting point S1 equal negative 50 and S2 equal negative 40, but the surplus variable should be greater or equal to 0. So that means it's not a basic, I don't have a basic feasible solution and a starting solution. So I have a problem here. To the way the simplex deals with this, if you have a constraint which is greater or equal, is to create an artificial variable or an auxiliary variable. So I add another artificial variable A1, and for the second one another variable A2. Adding the artificial variable will increase your feasible region. So to fix that, we add a penalty in the objective function. So since I'm minimizing, I would say plus m A1 plus m A2, where m is a very large number, like 10 million maybe. If the problem is maximization, I would subtract. Okay? And so the simplex method will solve this problem by driving A1 and A2 to 0. And so my optimal solution will go back. So my feasible region will be forced back into the original feasible region. We're not going to go more beyond this, and basically let the simplex method take care of this. In the next video, I'll start with deviations from standard form. Okay, thank you.